discriminative models into machine translation. All of them have in common that features are words or phrases. So it's a bag of words or bag of phrases. And classes consist of the whole language dictionary. And just one huge discriminative model is trained. So given a sentence, your features are the words in the sentence or phrases, and then from the model you get the ranking of the words from the or phrases from the target language. And all of them are implemented or are included in the phrase-based system Moses as the special feature there. Okay, so this is a insight into TectoMT system, how it works. So I work on, or I think most of us work on English to Czech translation within TectoMT system. So you start with English text and you want to get the Czech text. And first you must perform we perform an analysis that we transform English text from the surface level to the tree representation or tectogrammatical tree representation. So in this case, here is a branch, and this organization should help it. And when we have the English tree, we just copy it to the Czech side, and then transfer or translate the lexical units or lemmas, and also phonemes, but it's yeah. So this is the transfer. Then you get the Czech tree where this branch was incorrectly translated, and then you perform synthesis to get the surface text. So I concentrate on the transfer phase here, and this transfer consists of two models that interact with each other. And the first one is translation model and language model. Probably all of you know it from classical MT. But this language model, it is not just n-gram language model, but it's a three-language model. So it models how likely it is for two lemmas in the target language to be in the dependency relation. So you can ask Zdeněk or Martin for more details. So they use hidden Markov tree models, and okay. The other part, the one that I'm interested in more, is a translation model, and this is what you might expect, that given an English word, you obtain candidates or Czech candidates that are next re-ranked with language model. So when we want to train a translation model or any model, we need data. So in our case, the data come from Czech 1.0, which is Czech English parallel corpus, which is automatically analyzed and aligned. Yeah, it's parallel aligned, like on the textogrammatical layer. So we can easily extract all the features. So then you need features, of course, to extract. learning method, which you like, or whatever you like, and then you hopefully obtain a model. But in our case, this model, unlike what I mentioned in related work, we model not just single huge translation model, but it's a collection of separate models for every source lemma. So, given an English lemma, we collect all instances with this lemma on the source side, and then we train a model for this lemma with classes that are all target lemmas that were aligned with this English lemma. So we don't have a huge model, but we have a lot of smaller models. And if you are lucky, you can get such a model. Okay, so that was that is the translation model, and let me now introduce to you the individual parts, so learning features, what is in our case. So in learning, until recently, we used this CPAN module, max entropy. Inside this module, a batch learning, which is called this optimization method LBFGS. Don't ask me what it means. It's limited memory, L, and BFGS are acronyms for the surnames of the inventors, or I think so. And so it's fine, and it's batch learning. So you have to have all the data available when you want to train the model. Pros are that it's a CPAN module, so simple interface. It can be easily used in our Trix or in Perl environment. Cons or drawbacks are that it's not optimized for processing of tons of features or instances, and also that it's not completely or entirely implemented in Perl. It's the guts are in C++, but the C++ code is not available. So, for example, I don't know how there is a regularization parameter, but I don't know how it relates with the regularization parameter that is commonly used and is known as L2 regularization. So this is hard to find out. So this is what we used, and this is what I spend most of the time to integrate it into Perl or into Trix. It's Vowpal Wabbit. Aleš already mentioned it two weeks ago. So unlike the previous method, it uses online learning. It means that you just present this algorithm with instances, with examples, and in any time you like, you can take this model and use it and use the parameters trained. So you don't have to have all the data at the beginning and then train on all data and iterate over it. So you can also then adapt to what you see in the testing data, or what's coming from the test data or from the real examples. So pros, it's optimized for massive data processing. It was developed by big names in machine learning field, and it has a lot of parameterization options, like various loss functions, various types of regularization. Since it is online gradient online algorithm, you sometimes have to pass over the data several times to get better model. So you can like parameterize the number of passes through the data, and you can also use the batch algorithm LBFGS. The drawback is that to learn parameters, the learned parameters are not easily accessible because they are hidden in those C++ code, and it's hard. For example, if you want to cut the parameters, just filter out those which have small value that cannot influence almost nothing. So it's easily to cut this parameter, or these parameters in this way. It's hard to access it. And this is just I copy pasted it. So a comparison of how it's fast. So here is max entropy that we used. It was trained on subsample of 1,000 instances. So 1,000 instances are processed in 2 minutes, while in Vowpal Wabbit, 12,000 instances are processed in 7 seconds. And if I want to, I decided to run 5 passes through the data to get maybe the similar results as in this batch learning. So then it's still 33 seconds when you have 12 times or 12 times bigger data. So if I calculate it correctly, it's 48 times faster or 50 times faster. Yeah, it can vary, but it's faster. So I mentioned that I implemented it in 3 weeks, so not yet, but very soon you can use it on your own. It's this library. Now, for the time being, it supports just one against all multi-class learning, and also it is implemented as a batch learner. It means that inside the Vowpal Wabbit is online learning, but I first collect all the instances and then push it into the Vowpal Wabbit. It's because the task, when I collect instances for lemma, I don't know how many translation or Czech translation or classes it would have. So I first have to collect all the instances, then I know the number, how many classes are there, and then I can initialize the Vowpal Wabbit with the number of classes. So just because of this task, it is adapted to batch learner, but for other tasks, different tasks, you can use it as if I implemented it there, you can use it as online learning. And this is from my own experience, very important remark. Always shuffle your data before online learning. If you have sorted data, you can you very likely get a suboptimal solution because it's sorted, and in those loss function you get somewhere in some local optimum, but it's not the global optimum at all. So it's better to have it shuffled, or it should be. Okay, so that's all about learning. Now features. So this is the original set of features. I call it, for the sake of this presentation, local. It's a, oh, sorry. Since it's called local, it's very powerful. Or despite it's called local, it's very, very powerful. The scope of these features are current node and parent node and children nodes, and in the tree. I mean, so and preceding node in terms of surface ordering. So no sibling or no grandparent, just this very close neighborhood of the node, translated node, and the features then consist of, for example, lemma or formeme, grammatemes, capitalization, entity type, various features. So this was the basic set. And the set I proposed, the first one is context-based bag of words. So it's similar to what I mentioned in the related work. So, but the scope is different. In the related work, the scope was always the current sentence. Here I look further into the history. So the scope are two previous sentences, and actually I'm not looking into the future at all, so I don't have also, I don't have either the nodes that are coming after the nodes that I want to translate. And there is also one filtering that I just collect content words. So not to have there and the, which is, I think, not very important. And the qualities or the features are just lemmas. Another little set of features which I proposed, and Lukáš Žilka inspired me, is ESA concepts. So first I will explain what is ESA shortly. ESA comes, it's a explicit semantic analysis, and it comes from the field of information retrieval, and it's just the vector representation of text. So given a text, we obtain a vector of concepts and the weights of these concepts. And these concepts or dimensions of the vector are Wikipedia articles, and the weights are calculated as a TF, IDF, term frequency, inverted document frequency of the word in every concept. And if we have larger text, we collect all the vectors for every word, and we just compute the centroid of these vectors. And I used ESALib, the implementation in Java. Check it from Lukáš. Okay, so here the scope for these features was the same as in the previous case. So previous two sentences and all the lemmas, I just concatenated those lemmas, so I obtained the text, and then I push this text into the ESA library, which gives me concept or vector of concepts, and I select just 100 most prominent of them. So that's all about features and all about explaining the translation model, and let's go to the numbers. So, experiments. As I already said, training data was built from Czech, and for to have short experimental loops, I trained just on the 1/10 of Czech. It's still a lot of documents or a lot of sentences. And testing data was NewsDev 2009 dataset. And for all of the experiments here I'm going to present, there were the same parameters set. So these parameters were set to limit the size of the translation model. So because in case without any filtering, you train for every lemma you encounter. So it would be a very big model. So first I limit that minimum instances for the lemma must be over or equal to 100. And also with subsamples, so maximum instances for lemma are 1,000. It's for all experiments, so they are comparable. So it's the same set of 1,000 for all of the experiments. And we also cut features because I said that it's hard to cut weights or parameters in the trained model, so I decided to cut features, simply just features that occurred just once are not important for me. Okay, so evaluation metrics or measures. So intrinsic and extrinsic. Extrinsic I evaluated on like machine translation, so BLE, and intrinsic. You have an English word and you want to translate it. You get the translation and you just look into the reference translation, whether this translated word is contained in this sentence. So it doesn't rely on any alignment, it just looks what it's contained in the sentence. And on this I calculate 3 different measures. One is accuracy, where I count just the first candidate. From the translation model I get the ranking, and so I select just the best candidate, and if it's contained in the sentence, it's okay. If not, it's a mistake or error. And this accuracy is over all words. So unlike this defined accuracy, since we have some out of vocabulary words, so we have some undefined words or words for which we don't have model. So this defined accuracy is also the best candidate, but it's counted just over the defined words. And 5 accuracy is the same as the accuracy, but instead of 1 best candidate, I check first 5 candidates whether they are contained in the sentence or not.
So each of them has to be contained?
Not each of them. I get the ranking of, for example, branch, and I get pobočka, vietev with probabilities, and if pobočka is contained in the sentence, it's okay. It's if any of them from any of the 5 of them is contained.
And you use only one reference translation.
Yes. Okay, baseline. Here I'm gonna compare the learning algorithms, and in the first line there is a baseline, and baseline are just if we discard all features and we just count relative frequencies of Czech lemmas. So it's easy baseline, simple, and but this is very so maximum entropy and Vowpal Wabbit are like equally good, but baseline, we spent several years to to build this machinery, and we just improved 3% over the baseline, so it's like very discouraging. Comparison of feature sets. So this is what baseline is the same, local is local plus bag of words, and local plus ESA. Local plus bag of words is the winner. Local plus ESA is very poor, especially 5 accuracy is like very strange. Because like I must admit that it was very time consuming when I ran this ESA. I don't know whether it was because of I don't think it's because of the Java implementation. I think it's because of inter-process communication, or I don't know, but so therefore I ran just one experiment, and I have to work on this further. So forget about results of ESA here. I don't think it's going to be so bad in the future. In a translation scenario, we combine these discriminative models like trained with MaxEnt or Vowpal Wabbit with the baseline model, with the simple baseline model I've introduced, and we call it static here, and we interpolate based or combine by interpolation this static model with discriminative model. So in this experiment, I used the baseline model that is currently used in the translation scenario, and I combined it with either MaxEnt or Vowpal Wabbit with different features. And what can you see from this picture? That this is the weight of the static. So if it's 0, there is a drop to 42 or I don't know. So without static, it's poor. But if you introduce static, it's better to introduce just with a small weight. And especially for Vowpal Wabbit, where the weight must be really small. I guess that in Vowpal Wabbit, the distribution is more flat, and then this static more influences or affect the trend or the distribution. There was the static model alone on one single line. So is there any point in the weight? I thought that the 0 would be the point where No, this is not the same static. This baseline is built is built from the same set of feature as these models, and this static is one static that we use in the translation. It's built from whole chunk 0.9 or yeah.
If I ask and maybe answer also. So your baseline is. What were the undefined words? Those were for which you had either less than 100 instances of source lemmas or more than 1,000 instances. So
yes.
These are undefined, like if it's
In
rare word.
Yes, in this.
For all those models.
For all those models. But here,
Yes. Yes.
in this static, it's different, I guess.
So.
I don't know how it was trained.
Like, for example, if you have a very frequent word like to be, you have not trained a model for this with MaxEnt and other?
No. No, if you have a frequent word, you just use 1,000 of instances.
Oh, yes. So you don't disregard
No.
You just
subsample 1,000 or something around 1,000 instances.
Okay.
Because otherwise the MaxEnt, it would last for ages, and especially for B or AND, such lemmas.
So the advantage of static model is it was trained, let's say, on the whole chain, so even very rare words are contained then, and it serves mainly as a fallback.
Yes.
Okay.
The out of vocabulary for these models or the discriminative models are something around 20 or 15%, and out of vocabulary for static is just 8% or 6%. So.
The difference between the bag of words added to the model and MaxEnt and Vowpal Wabbit, does that say something about the scalability of the MaxEnt implementations? Like, if you add bag of words to Vowpal Wabbit, it's better. If you add bag of words to MaxEnt, it's worse.
Yeah. But I don't know why I don't know the reason. Okay. So now it's going to be more funny and fuzzy. Because here is the evaluation of static plus discriminative model. And in intrinsic evaluation, everything is okay. Static plus Vowpal Wabbit, local plus bag of words is the best. But in extrinsic evaluation, everything gets like shuffled. And now one of the best is static. And I really don't understand this. And I have to like spend some time and examine it more.
It would be very useful to show also the components of the blue score, so how many unigrams, bigrams, trigrams, and so on matched, and also a lemmatized blue. So that we would know if blue doesn't penalize you for picking some wrong form, but choosing a good word.
Yeah, but that happens like the picking of the wrong form in the later stages, or I think that should be the same. Or, I don't know. Because for me, model is the same.
Your last line may very well be the best model given the selection of lemmas, but these lemmas might get different forms than the reference requests, and therefore your blue score will decrease.
Yeah, it can be the case.
one possible explanation. In the extrinsic evaluation, there's also the language model. And if the distribution from the translation model is flat, maybe the best variant was ranked as the first one, but the second best was only with slightly lower score than language model may put the second best as the first best, change the ordering, and if it was the case that...
But it was similar when I turned off the
even without language model?
Even without.
Oh, so...
Yeah, so...
This is the explanation.
With just one short question, do you also have a blue score with using just the baseline of picking the most frequent Czech lemma?
It's static.
That's the static?
Yeah.
Okay. Okay.
So, yeah. I have to look into that more. And finally, learning curves. It's measured on the accuracy, or with the accuracy. So here are the number of Czech documents. So the total number of documents is 71,000. And
The blocks, it's like 10 or 15 sentences.
no, 71,000 documents, tricks, files.
200 sentences per...
200 sentences.
Yeah.
It's not documented in any logical...
No. Yeah, sorry. Yeah. It's just a, like, mashup of chunks. Yeah. So, okay. It doesn't look like normal learning curve, because for normal learning curve, the train should decrease while the testing on the test set should increase. But this increase of both is caused because of the minimal instances criterion or filtering. So if I test on the training data, I don't have a model for every word. So, and if I measure it with accuracy, so I'm also penalized for undefined words. If I measure it with accuracy defined, it would look similar, but in the opposite direction. That at the beginning, both will be around, I don't know, 60, and then decreasing. So, but we can see from this that that with enlarging or expanding data, we can get better on the logarithmic scale, but it's getting slower in the end, and I think it will get slower and slower in the improvement. But still we have this space to train on. Okay. So to conclude, so Vowpal Wabbit, the main message here, Vowpal Wabbit makes it possible to train on tons of data, and not only for MT. So it will be available, and you can use it or contribute and discuss some with me any improvements. And this is the discouraging point. That a lot of machinery makes just 3% improvement over the baseline, which is very simple. And bag of words seem to help, but just in the intrinsic evaluation. And from the learning curve, we can see that in the near future, we don't need Czech to 0. We still have a lot of data, a lot of unused data or unexploited data here. Okay, so and what to do next? There are a lot of things. So first with Vowpal Wabbit, make it available for you. Extend the Perl interface. For example, the method that Aleš used, it's not yet implemented or available there. So, but I already made it work in the C++. So I hope it will be available soon. Translation, for sure I have to find out why there are those strange BLE scores. And with features, limit the sparsity of especially I think with ESA, because just the local features are in average 20 features for every instance. With ESA, I add another 100 features that are very sparsely distributed, and I guess that's the reason of the drop. And yeah, I already told and ESA, I have to make it faster and to experiment it more. Okay. Thank you for your attention. And now it's your turn.
Thank you for your presentation, and I think we have some discussion during the talk. So, any other questions, comments?
Thank you for a nice presentation. And I have questions about the ESA, because
Okay, so
I want to ask how do you incorporate the features, or how do you use the concepts? Because you said you select just first 100 of the concepts, and what do you do with it?
just put it there without any weight. So first 100 concepts, it's numbers, and I just put it as a bag of words. I put it there, like one number, second number, without any weight. So there is no preference that this was the first concept and this was the second concept. It was just my baseline for the ISA, but then I struggled with it a bit. So
I see. Yeah, because like if you do this, it's equivalent to just using back of words. So I think this cannot add anything to that. Because like what you do, like you have the, for example, 4 million articles in Wikipedia, and what you did is you picked the first 100, which were back of words most similar to your text. But this was not why ISA was so good in measuring similarity, I think. So maybe if you take this into account, it might improve the crappy scores.
But I think still it includes or introduces new information, because just bag of words, you have to have the same word. Here it can happen that you have the same ISA concept, but there are not the same words in the bag of words that the concepts were calculated from.
Yeah, sorry, I was not completely right that it doesn't add any new information, but I think it's not very interesting information. But you will see how it goes in the future.
Yeah, it also introduces a lot of crap. That is not important, and I said it is sparse. Yeah, so.
I can help you with the faster
sure.
implementation, I hope. Thank you.
Thank you.
Okay, just a small question. So you said you look at 2 preceding sentences. So is there any good reason why not to look at the following sentences as well?
Because of the reason is just technical. Because I I've been working on anaphora resolution, and then you are interested just in previous sentences. So I just use the same module for this. But you can extend it to use also following sentences, and yeah. But when you use previous sentences, it's better if you want to use it in real time. So, but it's still far nobody are aiming into.
So I have a question related to the just 3% of improvement over the baseline. And the question is perhaps not only to you, but also to Aleš. The baseline by itself is not too high. Also one more remark. That's a point I miss in this to-do list. Like, have you looked at the actual words that the baseline doesn't do right, and what features would you as a human probably use to pick the right translation? So to what extent is the low score of the baseline influenced by the single reference you have? And to what extent is it really the issue of not being able to choose the right translation? And what features do we as humans use to choose the right translation? So.
Yes, I haven't looked into baseline, but I conducted that error analysis on TectoMT translation. And okay, I looked into, not into the baseline, but into those discriminative models, and a lot of times it's just wrong translation, but not wrong, but the other translation, but it's not in the sentence, in the one reference sentence, but it's equivalent if you use this translation. So it would never be 100%, of course, the accuracy. And if you have just one reference translation, and
can you guess? You don't have any numbers on this, but can you guess like what proportion of these errors of whatever model was there was almost correct translation, but definitely not accepted because of missing in the reference because of lack of reference? So would it be half?
I just skimmed through it, and I not half, or maybe half. I don't know. I have no idea for this. It depends on the. I think, for example, for if you have conjunctions, like despite, in spite of, or yes, so you can use them like. They are equivalent, and there are a lot of times that there was used another conjunction, and that was in the sentence, but it was still correct. And I also seen in the error analysis that TectoMT has a lot of problems with collocations, or since it doesn't incorporate phrases, it has problems with phrases or collocations. For example, driving license is split into driving and license, and then license can be translated as vodičský. It's you have just license, and one of the option is vodičský, as driving too. So, but that's something else. But it's a source of a lot of errors.
I have a question. Did you also try to incorporate features from a closer context, but specifying the position of the, like, the surrounding lemmas,
No.
3 previous lemmas, 3 following lemmas, say, on the surface, and like if you incorporated those features along with the indexes, you might even be able to kind of model the phrasal context using this discriminative model. So I'm wondering if you experimented with these features. And also, have you tried to distinguish the lemmas from the current sentence from the lemmas from the previous sentence? And
no, there's just bag of words and yeah, but there's also plan or there's a lot of options there. Also to try bigrams or to make use of the tree structure. So from the previous sentence, the parent child couples, for example. There's a lot of options there.
One more question: how long does it take to train VW on all these models, or on all these lemmas that you? How long does the whole experiment cycle?
Yeah, with this limitation on 1,000, maximum 1,000, it's very fast. Or like, I train it on clusters, so every job took just a few seconds. So, but you have to first, but it's fast. Then you just merge models and it's fast. But if you want, then if you train a model from all of the instances, then for example you train the model for AND, it will that's the bottleneck. So you end with all of the jobs, with all of the sentences, and there are still 2 jobs for AND and personal pronoun. Yeah. And it's training them like 50 times longer than others. So there should be also something like, or it could be something like to filter or to, if I have a lot of instances, not to perform 5 passes, but just 1 pass over the data, for example. I don't know. A lot of options.
Because you can't really model it. I'm predicting the correct translation of AND given all the
it's another case that
garbage collector words that were aligned to it and picking one from
If there's no questions, so thank you again. Thank you for your talk.
Welcome.